Hello everyone, today we will be going over a net positive suction head problem and figuring out where the pump should be placed to avoid cavitation. Let's begin. In our problem, it says that we have a 32-inch pump that is to pump 24,000 gallons per minute of water at 1,170 revolutions per minute from a reservoir whose surface is at 14.7 pound-force per inches squared absolute. If head loss from reservoir to pump inlet is 6 feet, where should the pump inlet be placed to avoid cavitation for water at 60 degrees Fahrenheit? And you have a vapor pressure value of 0.26 pound-force per inches squared absolute with a specific gravity of 1. And for part B, at 200 degrees Fahrenheit with a vapor pressure of 11.52 pound-force inches squared absolute and a specific gravity of 0.9635. In order to begin solving, we have to find our net positive suction head, or our NPSH. We do this by using the measured performance curve, which is in our diagram here. So to start, we can start at our 24,000 gallons that they give us, which is shown here, right? And then all we really need to do is come up to this curve where our NPSH value is, go about right here and then come over, and we see that here it's about 36 feet. So we can say NPSH is equal to 36 feet. All right, so we'll just hold on to that value because we'll need that in a little bit. So now that we get that, we can start to solve, okay? Our general formula for our NPSH is this equation. All right, and here in this equation, PI is your pressure at the pump inlet and VI is the velocity at the pump inlet, while P sub V is the vapor pressure of the liquid, and then rho is density and G is your gravity. So in this form, it's a little bit useless because we're looking for a height, and in this equation, there's no variables of height. So we can rewrite this equation using Bernoulli's. So we get something that looks a bit like this. And this can also be rewritten just to keep things a bit more simple. Okay, so that will be our equation. And PA is the free surface pressure, where ZI is the height of the pump, and H sub FI is the friction head loss. So since we pretty much have all of these variables given to us in our problem statement, we can begin to start plugging all of our variables in and then solving for what we need, which is the height. So we already know our NPSH to be 36, so we say 36, and then we can say and then to convert from inches squared into feet squared, we can use this little conversion factor here of 144, which converts from inches squared into feet squared. So this will be our full equation. And we can use an inequality here since 36 feet, which is our NPSH value, is a requirement value. So it's the required NPSH that you'll need for the problem. So we can use this inequality here to basically say that it can only be greater, or not greater, it can only be equal to or less than 36 feet. Any higher and you will guaranteed have cavitation in the water. So now we can rearrange this in order to solve for our height. This should come out to be this. Okay, so this is our answer for part A. So now that we have our answer with a height of 8.7 feet, this means for part A, our pump must be placed at least 8.7 feet below the reservoir surface in order to avoid cavitation. So now for part B, we can basically do everything we just did, except in part B, they tell us our specific gravity is equal to 0.9635. So in order to account for that in the next equation, we can do this cool little trick where we take that rho g value from earlier, which is 62.4. If you multiply this 32.2 feet per second by this 1.94, right? And we take that and then we multiply it by 0.9635, which is our specific gravity. And this should give us 60.1 pound-feet cubed. Okay, now we can just plug this into the same equation that we had here and solve again for Zi for part B. And in part B, nothing else is changing, so our NPSH value will also remain the same. The only thing that will change is this PV value. Use the same conversion factors. And then we divide it by our new rho g value. Okay, now we can do this and rearrange and then solve for Zi, which should give you something that looks like this. So this is now our answer for part B. And just like in part A, this will be the height that the pump has to be placed at or below that in order to avoid cavitation. Thank you guys for watching this video, and that is the end of this problem.